Welcome to Chapter 3 of the Deep Learning Fundamentals series. In this chapter, we focus on how neural networks actually learn from data. You'll discover the optimization problem at the heart of training, how gradient descent iteratively updates parameters, and how backpropagation efficiently computes gradients using the chain rule. We'll also cover practical training considerations like batch size, momentum, learning rate selection, and how to monitor training progress with learning curves. Training a neural network means finding the parameters theta star that minimize the loss function L of theta. This is written as theta star equals the argmin over theta of L of theta. Gradient descent solves this iteratively. Compute the gradient of the loss with respect to the parameters, then update the parameters in the opposite direction of the gradient. The gradient always points in the direction of steepest increase, so moving opposite to it decreases the loss. The learning rate eta controls the step size. Each update follows the rule. Theta becomes theta minus eta times the gradient of L. This simple iterative process is the foundation of all neural network training. Computing the gradient of the loss with respect to every parameter in a deep network could be extremely expensive if done naively. Backpropagation solves this by efficiently computing all gradients in a single backward pass through the network. The key insight is the chain rule from calculus. If the loss depends on a parameter through multiple intermediate computations, you can decompose the total derivative into a product of local derivatives. Errors propagate backward from the output layer to earlier layers, with each layer computing its local gradients and passing the error signal to the previous layer. This makes training deep networks computationally feasible. Let's look at the specific formulas each layer computes during backpropagation. For a given layer, 3 gradients are needed. First, the gradient of the loss with respect to the weights equals the gradient with respect to that layer's preactivation, multiplied by the transpose of the previous layer's activations. This tells us how to update the weight matrix. Second, the gradient with respect to the bias is the mean of the preactivation gradient across the batch. Third, the gradient we pass backward equals the transpose of the weight matrix, multiplied by the preactivation gradient. This last term is what connects layers together, allowing the error signal to flow from the output all the way back to the first layer. Each layer only needs local information plus the error signal from the layer above. In practice, we rarely compute gradients over the entire dataset at once. 3 strategies exist with different trade-offs. Batch gradient descent uses all samples per update, giving accurate gradients but requiring large memory and slow updates. Stochastic gradient descent, or SGD, uses a single sample per update, which is fast and memory efficient but produces very noisy gradients. Mini-batch gradient descent is the practical middle ground, using a subset of samples, typically 32 to 256. Mini-batches provide reasonably accurate gradient estimates while fitting in GPU memory and enabling efficient matrix operations. Larger batches give smoother gradients, while smaller batches add beneficial noise that can help escape local minima. Standard gradient descent can be slow when the loss surface has ravines, narrow valleys where the gradient oscillates back and forth. Momentum addresses this by accumulating a velocity vector that smooths out oscillations. The update rule has 2 steps. First, compute the velocity as v equals beta times the previous velocity plus the current gradient. Then update the parameters as theta minus eta times v. The beta parameter, typically 0.9, controls how much history to retain. Think of it like a ball rolling downhill. Momentum keeps it moving in consistent directions while damping oscillations. Directions where gradients consistently point get accelerated, while noisy directions get averaged out. The learning rate is perhaps the most important hyperparameter in neural network training. If the learning rate is too small, training converges extremely slowly, taking many epochs to reach a good solution. If the learning rate is too large, the updates overshoot the minimum, causing the loss to oscillate or even diverge to infinity. A well-chosen learning rate produces smooth, steady decrease in the loss function. In practice, many practitioners use learning rate schedules that start with a larger rate for fast initial progress and gradually reduce it for fine-tuning. Finding the right learning rate often requires experimentation, though techniques like learning rate range tests can help. An epoch represents one complete pass through the entire training dataset. Training typically requires multiple epochs because a single pass is not enough for the model to learn complex patterns. However, the number of epochs involves a critical trade-off. Too few epochs means the model has not learned enough from the data, resulting in underfitting with high error on both training and test sets. Too many epochs means the model starts memorizing training examples rather than learning general patterns, resulting in overfitting with low training error but high test error. The optimal number of epochs depends on the dataset size, model complexity, and learning rate. Learning curves are your primary diagnostic tool for monitoring training progress. By plotting the loss against the number of epochs for both training and validation sets, you can detect problems early. In a healthy training run, both curves decrease and converge. The classic sign of overfitting is when the training loss continues to decrease while the validation loss starts increasing, creating a growing gap between the two curves. The point where validation loss begins to rise is where you should stop training, a technique called early stopping. Learning curves can also reveal underfitting when both losses remain high, or learning rate problems when the curves are unstable or noisy. Let's recap what we covered in Chapter 3. Training is an optimization problem, finding parameters that minimize the loss function. Gradient descent updates parameters opposite to the gradient direction, and backpropagation computes these gradients efficiently using the chain rule. Mini-batch training balances gradient quality with computational efficiency. Momentum accelerates training by accumulating velocity in consistent gradient directions. The learning rate controls step size and critically affects convergence. Monitoring learning curves helps detect overfitting and underfitting early. In Chapter 4, we'll build on these foundations to explore advanced optimization techniques and regularization methods that make deep learning work reliably in practice.